Today we're going to be talking about our last type of inheritance, the one that's connected to our sex chromosome, so our X or our Y. Take a moment, look at the learning goals, and then start again when you're ready to continue. We've talked a little bit about sex chromosomes already, those chromosomes that determine our biological sex. Females have an X and an X. Men have an X and a Y. But what are the differences really when we're talking about these chromosomes? Well, for starters, the X chromosomes have a lot of genes on them, over 1,000. And so the ones on the X chromosome are very different than the ones on the Y chromosome. These are not homologous chromosomes because they have different genes. The Y chromosome only has a few dozen genes. So there's some that are on there that are unique to the Y chromosome. They're the ones that switch on that male programming during the development of the fetus, but they're not related to the ones that you would find on the X chromosome. When we're talking about sex-linked traits, we're talking generally about those genes that are found on the X chromosome and not the Y chromosome. And again, that's just because there's just so many more traits on the X chromosome that if it's sex-linked, it's usually connected to the X. Females, because they have two X's, they're going to be carrying two alleles for the sex-linked trait. Males only have one X though, so they only carry one allele. And this is one of the reasons why men are much more likely to get sex-linked diseases. Females, if they have two alleles, one of them might be normal and that might help them protect them from getting the disorder. But if males happen to have that on their X chromosome, then they have that disorder. There's nothing that's a protective factor there. Men are going to be getting that from their mother because the Y chromosome has to come from their father. So any kind of sex-linked traits they might have is going to come from their mother. So one thing that people have often said is if you want to have an idea if there might be a chance that someone you know, or maybe even yourself, are going to go bald, you should look at your mother's father. That might give you a little bit of an indication of whether or not it might have gotten passed down to you. So let's just take a look at what might happen in this situation. We've got a trait, something called hemophilia, and that's what happens when your blood doesn't actually clot the way it's supposed to. So people, when they cut themselves, rather than that blood slowing down over time, sometimes they'll just keep on bleeding out. Because we want to show that this is going to be a sex-linked trait, we're going to connect that to the X chromosome. This is really important because if you don't connect it, then you may lose what's happening in the offspring. So we always have to represent our X and our Y chromosomes, and Y only if it's a male. So a normal male would have that dominant H on the X chromosome and nothing on the Y, because again, the Y does not have the same genes. A male with hemophilia would have that recessive H on there. Now, this is something that is unique to females. Females can actually be carriers. If they're normal, that means that they have both of the normal alleles. But if they're heterozygous, so they have one normal and one of that disease trait or that sex-linked trait, then they can actually carry that and pass that on to their offspring, even though they may not be affected. So that normal X-linked trait, that allows them to have fairly normal functioning, but they're able to pass that on. And that's also a reason why you might have things skip a generation. For a female to be hemophilic or to have that sex-linked trait, she has to have both recessives. So that's different than the male who only needs to have that one X chromosome that's recessive. So take a look at the problem that we have up on the board. We have a man who has hemophilia and is going to have children with a female who is a carrier. And we've got to figure out, first off, what are the chances of having a child who is a son who has hemophilia. So we'll start this off the same way that we would all of our other problems with our legend. So we want to make sure that we have the sex chromosomes in there because that's going to have an influence over the gender of the child and their chance of getting the disorder. So we're going to have, as we mentioned before, that dominant one is going to be normal, and hemophilia is actually the recessive trait. So we've got our legend. Now we have to figure out what our parents are. Since the father has hemophilia, we know that he has to be carrying that H, that little h, that recessive, on his X, and he's going to have a Y chromosome. Now, the mother is a carrier, and so since she's a carrier, she's going to be normal, but she's going to be carrying that hemophiliac allele in her DNA. The dad can either offer that X with the hemophilia or that Y chromosome to his offspring. And the female can either offer that normal H or that hemophiliac H. So those are going to be our gametes. So let's plug this into a Punnett square. Here, we've got the father, and here we've got the mother. Going through the Punnett square, we can see that if we're looking for the chance of having a son with hemophilia, there he is. So we actually have a 25% chance of a son with hemophilia. I want to bring your attention to something because it's a little bit of a difference, but it makes a big difference when it comes to how you're doing this. So if you notice, I changed the question here. The question before was, what are the chances of them having a son with hemophilia? This question is a little bit different. It asks, what are the chances one of their sons will have hemophilia? Now the difference matters because not all of these are going to be sons. We actually only have these ones that are sons. So if the question is asking specifically about the chance that a son or the chance that the daughter is going to have something, we're only going to be looking at the sons if they're asking about sons, or the daughters if they're asking about daughters. So this is actually a 50% chance that a son will have hemophilia. This is why it's so important to make sure that we keep all of those X's and Y's in there so that we are knowing what the gender of the offspring are going to be, because that's going to influence their chance of getting a disorder. Now, one thing you should make sure that you never do, and I see that at times, don't put anything here. Sometimes when people see that a male has hemophilia, they want to add something there. But again, this is something that's connected to the X chromosome. And since the Y doesn't have the same genes as the X chromosome, we're going to leave that off. So take a look over the key questions and answer them and see how well you've understood the lesson for today. And I'll talk to you tomorrow.